Hey students, today I want to review comparing fractions with you. Being able to compare fractions is a very critical skill in your number sense. Um, it will help you later on to really think about whether your answers are reasonable when you want to add, subtract, multiply, or divide fractions in real life situations. And so I have three different types of scenarios up here because you'll have three situations where comparing fractions may be different from the other scenarios. And when we compare fractions, these are the symbols, the mathematical symbols we use, the less than, greater than, or equal to symbol. In every situation here, I have either two or three sets of fractions that I want to compare. And there are a variety of resources that you can use. Of course, at school, when we're at school together, we have these magnetic fraction pieces that you all use all the time. I also have these little fraction pieces that we also get out, and those little fraction pies that we use that Miss Cruz borrowed this year, and I didn't get to bring any home with me. But probably more than likely, if you're at home, you don't have those resources with you. In your NTI folder, I did send home this colored fraction strip page with you. And so you can cut those out and use them however you want, or you can leave them fully intact together. You can print out more. If you have a printer at home and they can copy, you can copy this down and print out another copy. I actually got this online. I just Googled visual fraction bars, and that came up in some of the images. So you can get online and print out your own versions of these as well if you need more. So yeah, let's do a little bit of comparing, okay? So as you have begun to learn about fractions and what fractions are, if you still aren't clear about what the numbers mean in the fractions, what the numerator and denominator means, you need to go back and watch my video of the overview of what a fraction is and the meaning of a fraction, okay? Because if you don't understand that, then comparing fractions is going to be really difficult for you to do. So, probably the easiest sets of fractions to compare is this first scenario that I have, where the denominators are the same, meaning those bottom numbers are the same. And in this case, that means that the size of the pieces are exactly the same size. And that only applies if your wholes are the same. So let's give this a real life story and situation and see if you understand what I mean. Let's talk about pizzas. So if I have 1/4 of a large size pizza and 3/4 of a mini size pizza, and I want to compare which one of those is bigger, then that's going to be harder to do because I called that one large and I called this one mini. So it would look something like this, large versus mini. Obviously, 1/4 of the large is probably still going to be more than 3/4 of the mini pizza. So when you're comparing naked number fractions, you're just going to assume that the wholes are exactly the same size. So for this sake, we're just going to assume that the wholes are the same size. Now, if you're reading a story problem, you need to make sure in the story that somewhere it's indicated that the wholes are the same size. So if you're doing your NTI assignment, assignment 4, option 1, you have a page that looks like this where you have to shade in these fractional amounts on the correct model. But then down here, you've got to do some comparing, okay? Notice that all of these models here are exactly the same size long, and they're the same width and length long. They're just the same size wholes, and they are just split up differently depending on what the denominator is, okay? So let's say we have 2 large pizzas. Now when you're drawing models, you're not perfect, you're human. Your models are not going to be perfect. Like I look at this and I'm like, it looks so bad. I'm going to just try to do as best I can and make them about the same size. I guess that's a little bit better, okay? So I've got 2 pizzas. They're both large pizzas. I'm going to split this one into fourths and this one into fourths again. So these are the same denominators, so the pieces are the same size. So I want to make sure that I draw my pieces the exact same way. Now, do both of these show fourths? No. This one shows fourths. These pieces look equal. This one does not. I did split into 4 pieces, but the pieces aren't equal. These are not fourths. In fact, these pieces are bigger than fourths, and these are smaller than fourths. So when you are making your models, make sure that when you're comparing fractions, that you are dividing your wholes in the same manner, or else it's going to be really hard to compare. And make sure your pieces are equal. All right. So 1/4 versus 3/4. Well, if I ate 1/4 of the pizza and you ate 3/4 of the pizza, I'm going to shade in 3/4 because the 3 tells me the number of fourths to shade in, and the 1 here tells me the number of fourths to shade in. Which one is more? Obviously, 3/4 is more, and so that's really simple. When your denominators are the same, you only are really comparing the numerators, and 3 pieces are more than 1 piece because the pieces are the same size, so I just have to think about the number of pieces that I have. And the same is true over here with 5/6 versus 2/6. I bet you can already think about which one is more, and if you want to use this visual fraction model that I sent home with you, find the sixth. 1, 2, 3, 4, 5, 6, so it comes about right there, versus 2/6. Well, 2/6 would just be these two. Which is more, 5/6 or 2/6? Obviously, 5/6 is more, right? So that's the easiest. Those are the easiest types of fractions to compare, or when the denominators are the same. Next situation that we have is when numerators are the same, so the top numbers are the same, or here, but the denominators are different. Once you understand what fractions are, these types of fractions are also very easy to compare because you only have to look at in one location, and that's in the denominator, okay? So let's say, do we want to keep using the pizza scenario? I'll be honest with you, if I want to draw a circle, fifths and thirds are a lot more difficult to draw to make equal pieces. So I would say drawing rectangles is a lot simpler way to compare these. So you want to make sure your holes are the same size. Let's use a candy bar situation this time. Okay, there we go. So I want to compare 1/5. So what does that mean? I need to split this hole into 5 equal parts. Fifths are kind of tricky, but once you do it so often, you see, I don't even like that. So you know what? I'm going to be as precise as I can and do a little bit better job. My piece is just a little bit bigger. 1, 2, 3, 4, 5. I'm not perfect. That's okay. So 1/5. Now I need to show 1/3. That means I'm going to split this hole into 3 equal pieces. 1, 2, 3. Still, it's a little bit tricky. But if you'll notice, the third is bigger than the fifth. And that's kind of like when you're learning about whole numbers, and you're just learning about like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, those whole numbers, you know, you learn like 3 is bigger than 5, right? But when it's in the context of a fraction, it's different. It's like the opposite of what you think. The larger the denominator, the smaller the pieces. And if you look at your fraction strips that I sent home, as the denominators increase in number, the pieces get smaller. So it's kind of like a revelation you have to have when you start learning about fractions, that it's like the opposite of what you've been learning so far. And it's only because it's in the context of a fraction. A fraction is division, and you're dividing those wholes into that many size pieces. And so when you have a whole that's the same size, like I have a Hershey's chocolate bar. I have 2 Hershey's chocolate bars, one of the same size. One is cut into fifths and one is cut into thirds. The thirds are going to be larger, okay? And so now understanding that concept, can you figure out which one of those is larger, 3/4 or 3/10? Notice the numerators are the same. So now you just got to think about the size of the pieces. Get this out. Which are larger, tenths or fourths? Fourths are larger, and you have a lot of them. This one is almost a whole, right? This one isn't even a half, okay? So 3/4 is larger. And that leads me into the next thing. I just kind of used, do you remember what it was called? A benchmark. When I was explaining this further, I used a benchmark fraction called a half. Benchmarks are just those fractions that are very easy to visualize in our heads. They're the most common fractions that we have, or the most common numbers that we have, like halves and comparing to a whole or comparing to 0. Those are usually the benchmarks that we use. Like, is it close to 0? Is it close to a half? Is it more than half? Is it less than a half? Is it a little less than 1? Is it more than 1? So we use those whole numbers and the benchmarks of halves to help us compare fractions easier. Sometimes we even use, when we get more fluent, we can even use fourths and 3/4 as benchmarks. As you get older, you'll see that you can start using fourths more as benchmarks too. But right now, you're probably best at using halves as your benchmarks. So 3/4 was more than half, 3/10 was less than half, therefore 3/4 is the larger fraction. So the last situation that we have, and this is the big 4th grade skill that we learn in 4th grade, when numerators and denominators are both different. What strategy do you have to compare fractions when both the numerators and denominators are different? And this first situation that I have here, 5/8 versus 6/12, there's lots of ways there's lots of strategies you can use. You can draw visual fraction models out and compare them, kind of like we did here. Number lines is another visual fraction model that you can use. You can use those benchmarks like I just shared with you. I'm going to write benchmark down here. And I'm going to use the benchmark of a half. Is 5/8 more than a half or less than a half? If you know what eighths are equivalent to and a half, you would know that 4/8 is the same as a half. 5/8 is more than 4/8, so that's more than a half. What about 6/12? 6/12 is exactly a half. So since 5/8 is just a little bit more than a half, we can conclude that 5/8 is larger because it's more than a half. So I'm going to just write my explanation here. 5/8 is larger than a half, and 6/12 is equal to a half. So I use the benchmark of a half. So therefore, 5/8 has to be larger. I'm hoping that comes back to you and that's making some sense. And that is a great explanation to use. That's perfectly reasonable. You don't have to do anything super special. You can just explain that in words, numbers, or labeled sketches. Here's another situation that we have. 2/3 versus 7/12. How are we going to compare those numbers? It gets a little bit more tricky, doesn't it? It gets a little bit more dicey. Because the numerators are different and the denominators are different. Are they both less than a half or more than a half? It's probably easy for you to recognize that 7/12 is more than half because 6/12 is a half, right? 2/3, that gets a little dicey and tricky. But if you're thinking about what's half of 3, well, that's 1 1/2. But I have 2 parts out of 3. So that's actually more than half. Both of them are more than half, so how do I know which one is more? That's where you can draw visual fraction models, like cutting these out or drawing pictures of these. So if I draw, but this is where you've got to be really precise and accurate. So 2/3. Here's 2/3. Now I got to make my hole for 7/12 to be exactly the same in length, exactly the same size. And now I got to split 7/12. I got to split my hole into 12s. Go ahead and split it into thirds. And then I'm going to split each third into 4 equal parts. 4 times 3 is 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now I'm going to shade in 7. 4, 5, 6, and 7. And it appears 1, 2, 3, 4, 5, 6, 7. The 7/12 is a little less than 2/3. So 2/3 is greater than. Remember, the greater than symbol opens up to the larger value, the larger number. So, and that is true. 2/3 is larger than 7/12. But what if you're a bad drawer and you're just totally not convinced? I'm going to write 2/3 here. Label my pictures. What if you're not convinced? There's some number relationships that you can also think about. And one other way to compare fractions is to make the denominators to be the same. And you might be going, whoa, Miss Lucas, how do I make the denominators be the same here? Remember about learning about equivalent fractions earlier in the year? We used egg cartons a lot to compare fractions or to make equivalent fractions. Remember doing that? Where we split the egg carton into 12 sections, and then we split it off differently in different ways, like to show 1/4 and things like that. So you can do the same thing, just like 1/2 has many different ways, many different values. If you look here, 1/2 is the same as 2/4, is the same as 3/6, 4/8, 5/10, 6/12. All of those, see all those lines split down the middle? Yeah, those are equal to 1/2. Those are equivalent fractions. So hopefully you're remembering that. We can actually turn these fractions into equivalent fractions with the same denominator. And some of you are probably recognizing, hey, I think I can turn thirds into 12s. And how could I turn these thirds right here into 12s? Well, if you notice here, I don't know if you can notice this, but my lines here kind of show the thirds. For every third, there are 4 12s in a third. Let me get these magnetic strips out. So 4 12s is the same as 1/3. See that? So if I split these into 12s, after all, I'm trying to do dotted lines. So you can see the difference. Okay, I don't know how well you guys can see that, but there are 4 12s there and 4 12s there. So 2/3 is the same as 8 12s. Now if you look here, here are my 2/3. If I skip down here to my 12s, I see the same line. 1, 2, 3, 4, 5, 6, 7, 8. 8 12s is the same as those 2/3. So now I can rewrite 2/3 as 8 12s. And then I will keep 7 12s the same. And guess what? Now I have the same size pieces, just like the scenario up here. My denominators are the same, but I have a different number of pieces there. 8 pieces, 8 1/12s is more than 7 1/12s. So that's another option that you can do. So you can use benchmarks, or you can draw visual fraction models, or you can convert both of the fractions to have the same denominator by finding equivalent fractions for each one with the same denominator. Okay? So far we've had either less than or greater than fractions. But some situations You have two fractions that at first glance they look very different, and you're like, they're not the same. They're not the same value. But then you get to looking more closely. Look at 6/8 and 3/4. When you can notice the same relationship between the denominator in one and the denominator in the other, and the same relationship in the numerators, then they're equivalent fractions, okay? And in this case, when I look at eighths and fourths, I can think about, well, if I divide 8 by 2, I get 4. The same is true for 6. If I divide 6 by 2, I get 3. Or if I wanted to look at it the opposite way, 3/4 versus 6/8, 4 times 2 is 8, 3 times 2 is 6. I'm multiplying or dividing by the same exact factor. When that is true on top and bottom, they're equivalent. They're equal to one another. 6/8 and 3/4 are equal to one another. And I can draw that out with a visual fraction model as well. And I think it's easier to see this with rectangles. And if you notice, when I was drawing this, I'm not sure if you caught that. Let me erase it. I know we've talked about it in class. I get so excited. When I split my model into eighths, I split it into half first, and then I split it into 4 equal parts. I've got my fourths right now, right? What did I do to get my eighths? I split each eighth or fourth in half, right? So I multiplied it by 2, right? 4 times 2 is 8. 3 times 2 is 6, right? So 1, 2, 3, 4, 5, and 6. There's my 6/8. Draw that 3/4. There's my 3/4. Look, they're the same because there are 2 eighths in every fourth. So, thinking about that ratio table relationship, that ratio thinking, 4 times 2 is 8, 3 times 2 is 6. So when they have that same relationship, the numerator and denominators, they're going to be equivalent fractions. When they have the same multiplicative relationships, meaning you can either multiply or divide by the same number. So I think that's pretty cool. So that's comparing fractions in a nutshell. These two ways, when you have these two situations, they're pretty simple. When you have this situation where both numerators and denominators are different, that gets a little bit trickier, and so you got to think about benchmark fractions that you can use, comparing it to like halves and wholes and nothing and 0, or using visual fraction models to draw them out, or number relationships like multiplying by the same numerator and denominator. Let me back that. Multiplying by the same factor, both the numerator and denominator, to get the other equivalent fraction. But anyway, I hope that helps. Let me know if you have any issues with that page. And then on the other side of the page is your story problems that go along with comparing fractions. Make sure you do RDW, please. RDW. Read carefully, draw a picture, use numbers or words, and then write a solution statement. Okay? So you have 3 problems where you're comparing fractions there. And then the who ate more, that can be a fun activity. Yeah, with a chocolate bar. So good luck. Talk to you later.